We've already heard lessons learned from several missions, and you'll see that many of the same lessons are learned over and over and again. And that, I think, is part of the point for today, that there are indeed common themes and that lessons from past missions are likely to be relevant to future ones. It's not that we're stupid and we never learn from the past, but that it's inherent in the kind of business that it is, that when you are going to new places, doing new things, making discoveries, that fundamentally it is a human enterprise and there are human universals. So you will see that in the lessons that I'm going to talk about, that there will be much that is very familiar. On the other hand, it is also true that circumstances change. Technical circumstances change. The political environment, external environment, programmatics, everything changes. So that when the gremlins are first showing up on your program, they will look different from the ones that people saw before. And the only hope is that you recognize them earlier. And hopefully that's what will happen if you listen to enough lessons learned, that you will recognize your problems early enough and that you'll be able to fix them with less pain than some people have experienced in the past. Okay, so NEAR was the Near-Earth Asteroid Rendezvous, and it was the first launch in the Discovery program. So one of the things I will talk about is a little bit of the history and the context so that you'll be able to have a better, well, to be able to put into context some of the problems and lessons that we actually took away. Okay, let's see. There we go. And you click on that somewhere. All right. So it was 1996 launch. It was the first NASA asteroid mission, dedicated asteroid mission. Went out, visited Mathilde. First visit to a C-type. It's a primitive, carbon-rich, probably asteroid type. Then Earth swing-by, and first attempt to go into orbit around Eros, not successful. The date is significant, and we will talk about that. Then back one more time around the Sun. Second attempt to get her into orbit around Eros, successful. And the little movie was the rotation movie on approach to our second attempt. This is a flyby movie from the first attempt. Okay. So I already said some of these things. It was the first asteroid mission, first visit, still the only visit to a C-type asteroid. First rendezvous, first orbital operations, and I'll get to this also, the first landing on an asteroid. Okay. So, okay, again, putting into context, NEAR was the, it was the first APPEL planetary mission, which was the first for NASA. It was a long time since any planetary mission had been implemented by other than JPL, so that was a first. Also, a little quaint thing was that NEAR was probably the first mission, first NASA mission on which the internet was widely used to post, for instance, the NEAR participating scientist AO. That may have been the first one that was ever posted on the internet. I remember being called into my management's office and being asked, how come I don't have a secretary and a file of all the letters and announcements and schedules that I sent out to my science team? And I said, oh, I'm not doing that, I'm using email. What? What is email? All right, so anyway, this is 1992, okay? Anyway, also NEAR was the first mission with an open data policy, because the history of data policies before was, well, Galileo, which was a proprietary data period, 1 year. The investigators owned the data for nominally a year, but often were reluctant to let other people use the data. So we were the first mission where we had to agree up front, it was an open data policy, no proprietary period. Our scientists, in fact, the whole science community was not used to that idea. How are they ever, the people who invest all this time to build the instruments and develop the mission and all that, they don't get any reward for doing that? Anyway, that was the view then. It created problems. But anyhow, we got over that. All right, so NEAR again was a faster, better, cheaper mission. It was it's actually one of the first of the faster, better, cheaper missions. You've already heard about that today. What are the characteristics? Faster. We advocated less than 36 months development. Actually, it came out several months faster than that. Also, you've heard it was fortunately, one of the good missions on Ed Weiler's list. Came in cheaper. And there was a lot of discussion when we first started out whether it was possible in this cost category to have a 3-axis stabilized spacecraft with redundancy and all that. Okay, it was. I'll get back to this, talk about it some more. Okay. It was implemented mostly at APPEL. It was not a PI mission. You should bear that in mind. I was not a PI. I was a project scientist in the Steve Saunders mode and Dennis Mattson mode. Okay. Project scientist. There was both a facility instrument science team and a participating science team. And it was implemented at APPEL with support from JPL also for navigation. Okay. One of the points I did want to make was that, and I'll come back to this too, is that the implementation was done in the standard way at APPEL, and that's one of the reasons why that's one of the good lessons to learn, is that you really don't want an implementing institution to completely change the way they do their business. So APPEL, this was the way that APPEL and actually a number of other, APPEL did most of its missions, and there was another previous mission I'll mention too that was done just around the same time as Near, that was Clementine, and small team, lead engineer method, and all these things were practices for small missions. Now, I did want to comment on the first point here is that lately NASA has moved away from the 36-month development and that you're now allowing a longer time. That's, okay, anyway, you're moving away from that. I don't know that's good, but anyhow, that is one of the ways the external environment has changed. Okay, another little history note. This wasn't one of the missions. I think it came up earlier. I was amused that I basically sketched out in a lab notebook in 1991 the basic layout of the spacecraft and what you would call the basic concept of operations. So yes, this was a mission. You could do that. And that is basically what we ended up doing, showing essentially that a spacecraft with fixed solar panels, without a scan platform, and with a fixed high-gain antenna could actually do the Near mission. And anyway, I took this to Bob Farquhar, who was our mission manager at the time, and he said, yeah, this might work. And sure enough, that's what we ended up doing. Okay. All right, so Near is all about, okay, just what exactly Near was about you don't care about. The interesting thing is that this is a slide, and all the slides, most of the slides I've shown so far are slides that don't exist in electronic form. They're all view graphs. So this predates PowerPoint. There was life before PowerPoint. Okay, so there's no PowerPoint slide like this. Okay. And what we measured, okay, composition, it's the usual kinds of things. Again, this is a scanned, I just scanned the original view graph along with its original typos. I won't even bother to fix them, doesn't matter. Okay. And, all right, these notions that we have here, the modular design, the distributed architecture, the heritage, the heritage components, and also the heritage data bus, all of these things are, commonly adopted as low-cost mission. I just wanted to show also our schedule. Tom Coughlin was our program manager. He made this schedule right at the beginning in 1992. Authorization to proceed was 93, just to give you an idea. He never made another chart. This was his only schedule chart. Can you imagine getting away with that these days? No. So times have changed. There's no question times have changed. Now, there was a more detailed schedule, but that was the only chart he ever made that, he never went beyond that. Okay, now let's talk about I'm going to start now talking about some of the lessons and some of the things we did, and good and bad. Okay. One of the things that was, it's nobody's fault really, but is that when we started the mission, and when that mission was actually approved by NASA, no one had any idea how to operate a spacecraft around a small body. We just didn't know. We had no idea what we were getting into. Nobody knew what we were getting into. And so that was, in some sense, the biggest leap into the unknown for Near. So, of course, when the mission was approved, we had even though, we named the target, but we didn't know the mass of the target. And because of that, there was no way to actually simulate the orbital operations. You had no idea how to... Any of the things you take care of for granted now, in terms of simulating your navigational accuracy, showing that you could actually get all the measurements that we were promising, we couldn't do any of it because we had no idea what the orbits were going to be like. Okay. And it was worse than that, actually. Okay, that's the good part. It was actually worse than that because APPEL as an institution, it turned out, also had no idea how to operate a planetary mission. We had to learn on the fly. That's what it's, I guess we'll say that in a moment. We had to learn in the course of the mission. That is also a lesson which I think NASA has learned very well. They will never do that again. Okay. All right, I've already mentioned Clementine. The main thing, this is an example of external pressure on your project, which you will face too, which was Clementine actually was implemented a little earlier than Near. They flew to the moon, and they were flying in orbit around the moon, doing great science with a tiny operation team. They had 8 people. So when we launched Near, we were facing constant questions. How come your team is bigger than Clementine's? Okay, so, and it was. And even so, I will argue our team was not big enough to do what it eventually had to do. So, okay, yet another lesson is PDS. PDS also, as I said, Near was the first science mission for a long time, I don't know, maybe first ever, to have an open data policy. And also there was the first mission that had to deal with PDS. PDS was established, I don't know exactly when, but during the time when we did Near. So we had to learn how to deal with PDS at the same time as PDS is trying to figure out what it really wanted. And so that, needless to say, created problems too. And also we had to convince our science team that it was important for them to figure out how to archive their data when they didn't really want to, because what they really wanted to do was to publish the data, especially since they were going to be sharing it with everyone, and they didn't want to be scooped, right? So anyway, this has created human conflicts which we had to deal with. All right, and again, now things are different now because PDS is established, and the sort of the procedures, and also the procedures are well set, and I think also the science community now is trained and expects to deal with PDS, so it's not so much of a problem now. Okay. Okay, so I talked about already many of these milestones: the Mathilde encounter, Earth flyby, the Eros flyby, which was supposed to be the rendezvous, the real rendezvous insertion and the landing, and then the science operations. But let me skip to that. I want to point out that this is a Tom Coughlin chart again. He actually talks about mission extras. That's a very important point to remember, that we were, yes, supposed to be a focused mission, and yes, there is folklore that says the job of a mission manager or a program manager or a project scientist is to just say no. It's that when requirements are set, they're just set, and then you say no. That's not what we did. Life is not really like that. And so even on the Near mission, we had a whole bunch of things we agreed to that were not in our plan. The Mathilde flyby, the whole flyby was one of them. We had to spend extra fuel to get out there. We had to actually undertake operations we never tried before that were frankly dangerous. Okay? And then we had to agree to go below, closer to the asteroid for low altitude passes, lower than we'd ever intended to, or ever guaranteed that we would, and finally landed on the asteroid, which is again, okay, and I'll try to explain why that was also something that caused a lot of anxiety, but it all worked, okay. Now, Mathilde flyby. This was a case where there was a lot of dissension on the team again, it was Bob Farquhar who came up with the idea that, hey, if we spend only 50 meters per second, we can get out there, we can do this, it's big asteroid, C-type asteroid, first time ever, fantastic science. Science team agreed, yeah, great science. Unfortunately, I mentioned some of the engineering concerns. In addition to the fact that, yeah, we're burning a not insignificant amount of fuel to get there. And it was before our first TCM, the big TCM that would enable you to get to Eros. Okay, so anyway, bottom line was there was a lot of anxiety and discussion, but in the end, I think we made the right decision, which is, yes, let's go for it. It was successful. It did work. All right. I say that also in context. That was June 1997. Then in December 1998, that was when we had our big problem. Okay, so this was the second burn of the main biprop engine. The burn shut down after 1 second, and immediately, of course, brought back memories of what happened on Mars Observer, which lost the mission. The mission was lost at the second burn of the big biprop engine because, well, most likely it's because of the migration of the oxidizer and, fuel causing the thing blew up. So we didn't know what happened on Near. Long story short, it was recovered 27 hours later. Spacecraft just contacted Earth. It was batteries fully charged. It was in sun safe. Fine. Okay, but what actually happened? All right. This is why the story is interesting. What actually happened? There was a whole series of events which the first 40-some minutes of it were recovered. After that, we don't really know what happened because there was a low voltage sense on the spacecraft, solid-state recorders were shut off, and the data were lost. So we don't know what happened toward the end. But there was a whole series of, let's be honest, they were just mistakes. And starting with, if I may go back, starting with the picture of how the spacecraft was fundamentally put together. It's right here. As you can see, is that the engine is here sideways compared to the, and the payload attached fittings on the bottom. It's inevitable in this too. The main load bearing structure is this way, and the main engine structure is perpendicular to that. So, when you fired that engine, it flexed. It flexed just enough to get a false reading of a lateral thrust on the accelerometer, and that's what shut us down. Okay. Now, the thing about it was that the data by which an analyst could have predicted that would happen, the data was actually down on the ground. We had it. It just didn't get where it needed to go for us to set the threshold properly. And then after that, the burn was shut down, command to sun safe. Turned out there was errors in the command script so that slew was done on thrusters. It should not have been done that way. It's done on thrusters, but then the thrusters were disabled in the command script. And then it had to take over on wheels. The wheels didn't have enough authority to stop the slew at the proper place, overshot. Then it demoted again because you overshot the Earth pointing, demoted again. And then there were more errors and ended up trying to sun point. And this is where the record becomes fuzzy. There were several, the Near had backup guidance systems, so it was switching back and forth between the primary and the backup system. There were a number of cases where it called autonomous momentum dumps. So there was, let's see, I think we counted 15, no, a total of more than 20 momentum dumps. Anyway, many switches back between the primary and we know those things occurred because that part of the memory was stored in a different part of the spacecraft. But anyway, the long story short is that there were lots of errors. These were all errors that all the testing that we did not turn up. Okay? We have a culture, APPEL is a culture of testing and the test and see fly and all that. That was deeply ingrained in our culture. Nevertheless, there were at least 4 errors that were not turned up by any of our testing. And so that's what caused the problem. Still, the system was designed with enough backup systems and redundancy that it recovered. We don't know exactly how it recovered, but when it next contacted Earth 27 hours later, the battery was fully charged, even though there was a low voltage sense, so the batteries are deeply drained. Batteries are fully charged, the spacecraft was completely nominal state. So it recovered. Exactly how it recovered, we don't know, but it did. So there are a number of lessons to be learned there, which, needless to say, APPEL has taken, this was many years ago, but we took them to heart, that the way the ops team operated, the way scripts are tested, the way also not only operation scripts, but the way that the guidance system is tested before launch, all these things, lots of changes had to be put into place because it showed us that some of the things we were doing were really not up to snuff. Okay, but those lessons have been taken to heart. Okay, so let's talk a little bit also about things that went right. Okay, the first asteroid landing is one of them. Remember the context of that. The first asteroid landing, well, not before we get to the landing, our rendezvous burn was at the beginning of year 2000. It was only a few months after the losses of the Mars 98 spacecraft. That was in late 1999. So you can imagine, this is another thing you can expect, that things that happen to other projects can have a big effect on you, because that's exactly what happened to us. In Mars, the Mars 98 missions were lost, and then all of a sudden it becomes, Near is about to take its second attempt after screwing up the first one, the second attempt to get into orbit around Eros. And you can imagine the kind of scrutiny we were under and kind of restrictions and the interest that we got at headquarters, exactly the kind of interest you don't want. But anyway, we had that. And so, fortunately, by the time we had a successful rendezvous, no problems, spacecraft never safed once during the entire orbital period, which was amazing. And when the time came for us to say, okay, went to headquarters again and said, we want to land the spacecraft. They said, no, you're not landing the spacecraft. We were allowed to command the spacecraft to descend to the surface, but we were not allowed to land. So I said, okay, fine, we will do that. We had Dan Golden actually out at APPEL, and when our ops team announced that, yes, the spacecraft was on the surface and we were still in contact with it, it took a while for that to sink in. It succeeded? So anyway, he was very happy about that. So things that went right, let's talk about that. Okay, what were things that went right? Some very important things here. First, the programmatic context. As the first launch and discovery mission, everybody needed Near to be successful. Obviously, APPEL needed it because it was our first planetary mission. NASA needed it to enable the discovery program to get off to a start, to enable it establish that it was a credible, useful, important thing to do with Congress and with the administration. Community needed it also. Okay, as I said, APPEL had a culture of doing this kind of mission. It was ready, with the one exception of not being ready for mission ops, but we had to learn how to do that. And the last thing, which is very important also, is that we had strong support from Wes Huntress, AA, all the way on down, from headquarters. They wanted us to succeed too, and we had very good relationships. I have to say, at the time, the program office at the field center did not exist, so we worked directly with headquarters, the program executives at headquarters, but we had good relationships with them. One of them was Paul Hertz, in fact. I don't know, guess he's not here. But that relationship is really key. Your program executives, it's been emphasized here, your headquarters contact is really, really important to help your mission go. Let me again, so some of the things that are here are the lessons that you have seen before. One of them is that in order to succeed, there's really a troika, the science, the engineering, and the management. They are all separate disciplines. They all have to be pulling in the same direction or you cannot succeed. And there's important lessons here. One of them is that you, the PI, you, the PM, nobody can do the mission by themselves. You need the whole team. And that's really key. So, And as people have said before, you have to make your decisions in a timely manner, because once time is spent, it can never be recovered. Once money is spent, time is money, and the meter's ticking. The worst thing that can happen is to be waiting for someone to make a decision, because other people are going to be waiting too. Your engineers will just reach a point where they can't continue, and nothing is happening. You're paying, but nothing's happening until you make a decision. And we've heard this many, many times. The key is communication, so I put it at the top of the list. And the most important thing about it is the requirements, is understanding them. It's not, all of you have a pretty good handle on your requirements already, or you wouldn't be here. But the point is that it's not enough for the people at the tables to know what the requirements are and to understand them very deeply, not only what they are literally as a letter of the law, but where they come from and how they bear on what the mission is supposed to be doing. You've got to have your working level people understand that too. Your subsystem leads and even the people at lower levels than that, because every day there are decisions they have to make, how to do something versus another way to do something, and if they don't understand your requirements, they may create a problem that you won't find out about for a long time. And many of you have experiences already in which it will turn out that an engineer comes to you, they really have a problem with doing something a particular way because they interpreted the requirement as forcing them to use a particular device or meet a particular requirement, and then you will tell them, I actually don't care that much about that. All right, you can relax. You can relax that a little bit. All of a sudden, their life is a lot easier. So this is the kind of thing you have to watch out for. It's the understanding of the requirements at all levels of your team. It's also understanding your priorities. Okay, I've already talked about this, and the no surprises. You can't even a lot of the same words. The interfaces are very important, and it's not only at the system engineering level, high level. It's at the people level too. It's the way of the institutions. One of the key things about one of the conflicts that people can run into is that your engineers and your people, even your project managers, they have to report to a line management at their institution in addition to the project management. And those interests are not always in alignment. That can often be a source of problems in a program. Typically, it has to do with institutions believing that certain things have to be done certain ways. This is not only just a mission assurance issue, this can also be a mission issue of wanting certain kinds of work to be in certain places. This is a commonly encountered problem you may have to deal with. All right. Then the other issue we've talked about is exactly what your requirements are and what they mean when you go beyond them. So, yes, we heard the aim high. Yes, you have to do things that have never been done before and all that. At the same time, that's where judgment comes in. How high do you aim? And there is such a thing as a 2 miracles rule. You may have heard that you can get away with 1 miracle, but often you don't get away with trying to do 2. And by miracles, I mean something that is a big step forward in the state of the art. It's something where you need an invention or your discovery, it's a problem, or it's something that you actually don't really know how to do when you start out and you say, I'm going to have to figure this out. I'm going to discover something. Okay, now, were there miracles on Near? I would say yes, there were. I think the biggest one was, in fact, our guidance system. That Near was, again, one of the first missions that ended up was designed with the autonomous capability to point to a fixed latitude and longitude on an irregularly shaped rotating body. Did not have to be continuously pointed to inertial, you didn't have to give it a sequence of inertial pointings. That was the first mission to be done that way. And that's a big innovation. It's amazing that it worked. I'm still amazed it worked. But that was our 1 miracle. Okay. And the last thing I think is, yes, process. Following process, doing things the way things, following a fixed procedure as opposed to relying on people who, I call them heroes, people who have amazing capabilities but who need them because they're always in a position of having to make a diving catch, fix a problem they discovered, maybe they caused even, but they can fix it because they're so amazingly wonderful. Okay, you have those on every project, And just beware that heroes don't always survive. Heroes also don't always make the catch. So anyway, I should stop probably.
Thank you very much.